In the previous lecture, we have gone through the op-amp transfer characteristics with high gain. If the gain is extremely high, what happened? We have seen the transfer characteristics are something like this, and the linear region of operation is very less. In case of op-amp with open loop configuration, it is V minus, V plus, and we call this one as VD and V output. Okay, the slope here I took theta, the angle slope is tan theta, and gain is some 10 power 4, means theta is 89.98 degrees. The linear region is very much less. Okay, very less linear region, around 1.5 millivolts to minus 1.5 millivolt. Within that range only, I can write V output is equal to A into VD. Of course, here A is equal to 10 power 4. We have gone through this. And if A is infinity, then it's a perfect vertical line and there is no meaning of linear region. At least we can say small portion of linear region where you can relate output and input by means of an equation. V output is equal to A into VD. If gain is infinity, then the transfer characteristics are like this. Then what you can do, you can just, it behaves like a comparator instead of a differential amplifier. VD is greater than 0, output is Vsat, and VD is less than 0, output is minus Vsat, which is an example for an unstable system. So in control systems, we studied if the gain is large, extremely large, then the system becomes less stable. This is one such example. The gain is less, then you can able to see some linear relation between output and input. But once the gain is extremely high, output cannot approach infinity. It practically reaches its extreme values of plus Vsat and minus Vsat. So to improve the linear region of operation in op-amp, we need to apply some feedback. Okay, it is a simply open loop system. No feedback in this particular case. Now I would like to apply feedback to this operational amplifier. Okay, how does that feedback circuit appear? See, in control systems, if you take it, it's an open loop system. Some xi is input and x0 is output. Then closed loop means what we do, it is open loop system. We have some feedback network. It is also known as beta network. That x0 is acting as input to the beta network, and a part of the output xf, it is xi, we call it as xs, plus minus. Of course, minus or plus, anything you can write here, depends upon. Then it is called closed loop system. Okay, feedback network xf is equal to, we call it as beta times x0. That means it is a part of the output is fed back to input. This is a closed loop system. Okay, it's a gain of an amplifier instead of I can write sorry, some amplifier A, let me write it like this. Then open loop system. Then to this amplifier we are applying some feedback, and this is what is known to us. The similar story I'm taking here, like I'm taking the operational amplifier plus minus. It's an open loop system, V plus V minus, and this is VD. V output is equal to A into V plus minus V minus. We are well aware of it. And of course, it works with the presence of two power supplies, VCC minus VCC, we can write it. Now, feedback network means I am applying some feedback to the op-amp like this. R1, R2. So, this is a feedback network. See, the circuit is like this. This is a simple feedback. This is V output and means the voltage at this point with respect to ground, or I can say voltage at this point with respect to ground. It is V output, and VF is voltage across R2. Instead of X naught, I am writing V naught, and instead of XF, I am writing VF. So, if you observe this circuit, whatever the current that comes in this direction, entire current will go down only. The current entering into any of the input terminals of the op-amp is zero due to infinite input impedance. Then what is VF in terms of V output? Using voltage division rule, VF is equal to V output into R2 by R1 plus R2. We can write. VF means it is just nothing but voltage at the inverting terminal. So V minus or VF are one and the same. Now, right, we do not know as of now what kind of feedback it is, because we have two types of feedbacks, negative feedback and positive feedback. With negative feedback, the gain decreases and the linear region of operation will increase. With positive feedback, the gain increases. Already it is infinite. What will you do if it is positive feedback? Right, open loop configuration output is plus or minus V set. With a positive feedback also, the gain does not change. Infinity plus something, still it is infinity. The output should remain as plus or minus V set. Okay, how does but we do not know whether this particular case is a negative, is an example for negative feedback or positive feedback. But as far as this circuit is concerned, I can write V minus is equal to V output into R2 by R1 plus R2. Okay, in this circuit, I apply input at the non-inverting terminal first. Later, I apply input to inverting also. We will check what happens. The same circuit I am rewriting here with some input. V minus, V plus. Here I am applying some input and V output here. Entire current is going like this as I told. So VF or V minus both are same. We know that V output is equal to A into V plus minus V minus. Okay. So from this, what we can understand is, okay, let me take it as equation 1 otherwise. Next, what about V plus? It is VI. And what about V minus? It is V output into R2 by R1 plus R2. Let me take it as equation 2. Okay. In this, I give a fixed input. V input may be some 1 volt or minus 1 volt, some fixed value. I would like to keep it aside. V plus is a fixed value. And V minus and V output. Now, from equation 1, what we can write is V output is proportional to 1 by V minus. Actually, it's a negative sign. Means V output is inversely proportional to V minus. And the second thing is from equation 2, I can write V minus is proportional to V output. V output increases, V minus will increase, and V output decreases, V minus will decrease. Whereas if V minus increases, V output decreases, or V minus decreases, V output will increase. That is an inverse relation. This is very, very important point to be observed. Okay. Now I am applying some input. VA is equal to 1 volt, means V plus is equal to 1 volt. I am giving here some 1 volt. Then V plus is increasing, means definitely V output will increase. As V plus is increasing, V output will increase. If V output increases, what happens to V minus? So because of this V input, V output is increasing. If V output increases, what happens to V minus? It is V output into R2 by R1 plus R2 implies V minus will also increase. Anyway, input is constant at 1 volt. Keep it aside. If V minus increases, what happens to V output? If V minus is increasing, then, or in this equation, if V minus increases, V output starts decreasing. This increase in V minus does not influence V plus, no doubt about it. V minus increases means that reduces V output. If V output decreases, then what happens to V minus? It will decrease. V minus will decrease. If V minus decreases, then what happens to the output? Output starts increasing. Again, if V output increases, what happens to V minus? V minus will increase. V minus increases, V output will decrease. See the interesting point here. Continuously or alternatively, right? One step, V output increases. See, V output increases, then V output will decrease. Again, V output decreases, and sorry, here there is a mistake. This is very important part. I should not put you in confusion. We know this point. Suppose I am applying V input of 1 volt, means V plus is 1 volt, which is a constant value, which can neither increase nor decrease. Keep it aside. Then as V plus is increasing, definitely V output will increase, which implies V output increases. From this equation, I can write. If V output increases, but from 2, what I can write? V minus will also increase. If V minus increases, again coming back to this, V minus increases, V output is decreasing. If V output decreases, V minus will automatically decrease. If V minus decreases, then output will increase. If output increases, again V minus will increase. If V minus increases, V output decreases. So alternatively, if you observe this, in one step the output is decreasing, but again it is increasing. Next again it is decreasing. Next what comes? As V output decreases, V minus will decrease. V minus decreases means V output will increase. So if you want, you can even write that statement as well. So V output decreases, V minus will decrease. V minus decreases, V output will increase. As a whole, what you can understand is, it looks like output is increasing, decreasing, again increasing, decreasing, like this alternatively. The same thing we can see even for V minus also. Decreases, increases, again decreases, next it will increase alternatively. Finally, what happens? Both V minus and V output will neither increase nor decrease. Finally, both V minus and V output will neither increase nor decrease, and they settle at fixed values. What are those fixed values? We will see later. At this stage, nothing to worry. Okay. And here I took an example of input is equal to 1 volt. It's not mandatory to take 1 volt. You can take minus 1 volt also. Doesn't matter. The story remains the same. V input is minus 1 volt. You just take that also. Doesn't matter. Okay. Everything remains the same. V output is equal to A into V plus minus V minus. And V minus is equal to V output into R2 by R1 plus R2. These two equations do not change. Okay. Now input is negative means input looks like input is decreasing. If V input decreases, then V output will decrease. I can say if V input is equal to minus 1 volt, that is V plus, then is as it is decreasing, that makes V output to decrease. V output decreases means what happens to V minus? That makes V minus to decrease. If V minus decreases, then output will increase. If V output increases, V minus will increase. V minus increases, V output will decrease. V output decreases means V minus will decrease. And V minus decreases means V output will increase, which means V minus will increase, which reduces V output. So alternatively, because of this inverse relation. So here output is inversely proportional to V minus, but V minus is proportional to V output, and hence V, if you observe V output and V minus, they will neither increase nor decrease. In between, input is at a fixed value. It is meant for triggering the circuit. That's it. It won't do anything beyond that. Just it is triggering the circuit. Later, V output will influence V minus and V minus will influence V output. They both keep on increase, decrease, increase, decrease. Finally, they can neither increase nor decrease. They settle down at some fixed values. What are those fixed values? We need to calculate. We'll see that later. Okay. This is what we can understand from this. Keep it aside. Okay, you can give input at the non-inverting terminal, or you can give input at the inverting also. If you want to give input at the inverting terminal, what you need to do means you cannot just give the input at the inverting terminal like this. Okay, here you can apply input to the non-inverting terminal directly this way, but as far as the inverting terminal is concerned, you cannot give the input directly here. Because of this feedback network, what is the way to apply input at the inverting terminal? See this. R1, R2. Let us connect the non-inverting terminal to ground. And instead of connecting input to the inverting terminal, we can give the input here. Okay. In that case, what is V plus? It is 0. What about V minus? For finding V minus, you can take the node equation here. Right. You can take superposition also. So here, if I take node equation at inverting terminal, KCL at inverting input terminal, what we can write? V minus minus V output by R1 plus V minus minus Vi by R2 is equal to 0. And no current flows in this direction, we are well aware, due to infinite input impedance. Okay, op-amp does not load the input. Okay, further, V minus into 1 by R1 plus 1 by R2 is equal to V output by R1 plus V input by R2. Then V minus into R2 plus R1 by R1 R2 is equal to V output by R1 plus V input by R2. Further, V minus is equal to V output into R2 by R1 plus R2 plus V input into R1 by R1 plus R2. The equation of V minus will change. Earlier V minus is equal to V output into R2 by R1 plus R2. Now this is the additional term we are getting. This is one way in which we can write the output. V minus equation. But V output is equal to A into V plus minus V minus. That is well known thing to us. And there is another way to write what is V minus. Right? Alternative method is superposition. I write here. Alternatively, just for the better understanding of students, I am writing these many things, but to be frank, not required. Anyway, it is connected to ground. V output. So entire current is going like this. Or this circuit, because this current is 0, we can redraw the same circuit like this. This is V minus. So apply superposition, because right entire current is going between output to input. I can apply superposition. Means while studying the effect of V output, connect this one to ground, R1, R2, and it is V1 minus. How much it is? Voltage division rule, V output into R2 by R1 plus R2. Entire current goes down like this. Similarly, while studying the effect of V input, I can set this point to ground, R1, R2, VO, right, R, okay, V2 minus, what is this value? Entire current will go down like this now. V input to ground. Now again voltage division rule. How much do you get? Voltage at this point with respect to ground means voltage across R1. What it is? It is VI into R1 by R1 plus R2. So overall V minus is equal to V1 minus plus V2 minus. It is equal to V output into R2 by R1 plus R2 plus Vi into R1 by R1 plus R2. The same result we can see here. Okay, there are a number of ways to get the things. It's not an issue. Okay. So now if I take the circuit again, it is connected to ground. Vi R2 V output, V minus V plus. So what we observe is V output is equal to A into V plus minus V minus. Equation 1. And V minus is equal to V output into R2 by R1 plus R2 plus Vi into R1 by R1 plus R2. Here also 1 implies V output is proportional to 1 by V minus, means inversely proportional, and 2 implies V minus is proportional to V output. Of course, V minus is proportional to input also. It's not a big deal. Okay, done. Then if my input is equal to, if V input is equal to 1 volt, then means as input is increasing, what happens to V minus? V minus will increase. Okay, V input is increasing, V minus will increase. If V minus increases, what happens to the output? Output will decrease. Okay, here also output is inversely related to V minus, but V minus is directly proportional to V output. Okay, so input is increasing, V minus is increasing, that makes V output to decrease. Okay, as V output is decreasing, what happens to V minus? That will also decrease. Okay, output is decreasing, then V minus will decrease. V minus decreases, the output will automatically increase. Right, it is decreasing and output is increasing. If V output increases, V minus will increase. V minus increases, V output will decrease. Okay, so and V output decreases means definitely V minus will decrease. So we can observe that alternatively output is right here, output is increasing, next step decreasing, next step. Okay, I can start with output decreases first step, second step it is increasing, third step it is decreasing. Okay, and V minus, if you see, first step it is decreasing, second step it is increasing, and third step it is decreasing alternatively. So what you can say, output and V minus are neither increasing nor decreasing. They settle down at fixed values. Whether you apply input to the non-inverting or inverting terminal doesn't matter, but we have a feedback connection from output to inverting terminal. Okay, the feedback is from output to inverting terminal. In that context, V output is inversely proportional to V minus, and V minus is directly proportional to V output, which cause the output voltage and V minus to neither to increase nor to decrease. Keep this point in mind. Next, instead of taking connection from output to inverting terminal, I will take connection from output to non-inverting terminal. We can draw the circuit in any fashion we like. It is not mandatory to show inverting terminal on the top and non-inverting terminal at the bottom. Okay, output. Okay, and here I have taken an example of input is equal to 1 volt. If you want, you can continue with input of minus 1 volt, doesn't matter, right? Or you can take, if V input is equal to minus 1 volt, you feel bored, right? If I keep on writing all examples continuously, right? Not required actually. Anyway, so if V input is minus, so it is decreasing. V input decreases, so V minus will decrease. If V minus decreases, what happens to the output? Output will increase. V minus is decreasing, output will increase. If V output increases, then V minus will increase. V minus increases, then V output will decrease. V output decreases means V minus will decrease. V minus decreases, V output will increase. V output increases means V minus will increase. So alternatively, you can see here. It's not mandatory that it is valid only for input positive. Okay. My concern is you may apply input at the non-inverting or inverting terminals, doesn't matter. Okay, and the input may be positive or negative, doesn't matter. When there is a connection from output to inverting terminal, then this is the thing. Output is inversely proportional to V minus and V minus is proportional to output. This makes the output and V minus neither to increase nor to decrease. Okay, that is the interesting observation. Now I am taking a feedback connection from output to non-inverting terminal. Okay, here what happens? As usual, no current enters in this direction due to infinite input impedance, and entire current will go like this. So now I can write it is V plus. So what is V plus? It is V output into R2 by R1 plus R2. Okay, and V output is equal to A into V plus minus V minus. So let me take this as equation 1 and this as equation 2. Okay, here what happens? V output is proportional to V plus from 1. Again from 2, V plus is proportional to V output. Here both are proportional to each other. V output depends on V plus and V plus depends on V output. Both are directly proportional. Okay, so how it is influencing the system's behavior? See this. Now let us apply input at the inverting terminal. It may be a positive or negative input, doesn't matter. Let me apply some positive input here. It is V minus, it is some 1 volt, V output and V plus. Okay, so now V plus or V feedback, right? It's a feedback network. As I mentioned earlier, I need not write it again and again. This is our feedback network and this is V output and VF. Okay, then V output is equal to A into V plus minus V minus, and V plus is equal to V output into R2 by R1 plus R2. As I said, V minus is equal to V input. For example, my input is equal to 1 volt. If Vi is equal to 1 volt, that is V minus. So initially V minus is increasing. As V minus increases, what happens to V output? That makes the output to decrease. If V output decreases, V plus will automatically decrease. And if V plus decreases, V output will also decrease. See, my input is at constant only, is kept at constant. That's meant for triggering the circuit. That has triggered the circuit, that is making the output to decrease. Once the output decreases, V plus is decreasing. When V plus decreases, then V output will decrease. V output decreases, again V plus will decrease, and V plus decreases means output will decrease. Both are supporting each other like anything. V output is decreasing. Oh, immediately I will also come down. That's what V plus is. V plus is decreasing, then output says I will also come down. Both keep on decreasing. And finally, what level they can go? Both are decreasing continuously. And it is in like an infinite loop. Okay. So, is it possible for them to keep on decrease and go up to minus infinity? No. And to what level output can fall? And finally, V output falls up to V output minimum. It keeps on decreasing and falls up to its minimum. That is just nothing but minus V saturation or minus VCC if you look at the power supplies of this operational amplifier. And if you take this V plus, what it is minus V saturation into V output into R2, no, R2 by R1 plus R2. That's it. That's to that level VA will fall down. So this is true if my input is 2 volts or 3 volts or 1 millivolt or 1 microvolt. This is true. Input is positive. You are applying a positive input to the inverting terminal. The corresponding output should be no doubt negative, and it is of course my negative V saturation. Okay, that's what you can take. This is true with 0.5 volt or 1 millivolt or 1 microvolt. This is true. Just you are giving some positive input, and simply independent of the value of input, whether it checks whether it's positive or not. It's positive, then it leads to a negative output. That's it. And similarly, suppose my input is minus 1 volt, that is V minus. So it looks like V minus is decreasing. Then what happens to the output? Output will increase. If V output increases, then V plus will increase. And if V plus increases, V plus is increasing, then again output will increase. If V output increases, again V plus will increase. Both are supporting each other. No? V plus increases, V output increases, which makes V plus to increase continuously. V plus increases, again V output increases. V output increases, V plus will increase. Both keep on increasing. And finally, what happens here? Finally, V output rises up to V output maximum, which is just nothing but V saturation. Ideal value of V saturation is VCC. And if you want, you can write what is V plus, means it is V saturation into R2 by R1 plus R2. This is true even for minus 2 volts, minus 3 volts or minus 1 millivolt, etc. Input is negative, that's it. You are giving a negative input to the inverting terminal, output should be positive. And what is that positive value? It is saturation. Okay, that's what you can say. Why it is happening so? Because here the statement is output is proportional to V plus and V plus is also proportional to V output. In that case, once output starts rising, V plus starts rising, and output finally goes to V saturation. Once output decreases, V plus decreases, and finally the output goes to minus V saturation. This is the interesting point. Okay, and one more thing, here also we need not worry about applying input to inverting terminal. You can apply to non-inverting as well. Non-inverting means here you can't apply directly, you have to apply through this point. Okay, so I'm taking that case. So ground is not present. No, I need to apply input here. And inverting terminal is connected to ground, means V minus is 0. And what is V plus? Like the previous case only. Here no current is possible. Entire current goes like this only. If that is the case, what can I write for V plus? V plus is equal to V output into R2 by R1 plus R2 plus V input into R1 by R1 plus R2. You want, you can apply superposition, or you take the node equation here, the same result we get. Okay, the only concern is earlier I wrote V minus is equal to this given by this. Now I'm writing V plus is given by this equation, nothing else. Okay, now we have the two equations, that is A into V plus minus V minus. Let me take it as equation 1 and this one as equation 2. From equation 1, what I can write is output is proportional to V plus, and equation 2 implies V plus is again proportional to V output. Is there any change in this? No. Okay, whether you apply input at the inverting or non-inverting terminal doesn't matter. Output is proportional to V plus and V plus is proportional to V output. Now you give the input. If my input is equal to 1 volt, means I am giving some positive input. As V input is increasing, then V plus will increase. V plus increases means V plus is increasing, definitely V output will increase. If V output increases, V plus will increase. Again, V plus increases, V output will increase. Anyway, this is not changing now. Wherever you apply input doesn't matter, but V output and V plus are proportional to each other. So finally, what happens here? V output reaches its maximum value, that is V output maximum. What is that value? It is V saturation or VCC. So you have given a positive input to the non-inverting terminal. Output should also be positive, no doubt. And positive, what is that value? It is V saturation. And this statement is true for 2 volts, 3 volts, or 0.5 volt, or 1 millivolt, or 1 microvolt. Just the input you are giving is meant for triggering the circuit. Once the trigger is secured, and V output and V plus keep on increasing and reach the extreme values. And if you want, you can write here V plus is equal to, how much we can write? It is V saturation into R2 by R1 plus R2 plus, if input is 1 volt, 1 into R1 by R1 plus R2. Right, I am just writing VI into R1 by R1 plus R2. It depends upon the value of VI. This is what we can say. Okay. Next, input can be negative also. The same story repeats. If VI is negative minus 1 volt. Okay, so it looks like input is decreasing. Anyway, V minus is 0. I need not worry about it. So as input decreases, V plus will decrease. If V plus decreases, V output will decrease. V output decreases, V plus will decrease. Again, V output will decrease and V plus will decrease. And finally, V output falls to its minimum value. V output minimum, it is equal to minus V saturation or minus V CC. And what about V plus? It is minus V sat into R2 by R1 plus R2 plus Vi into R1 by R1 plus R2. That's it. I need not worry much about it. So what we can conclude is we have two types of connections. The connection is from output to inverting terminal. In that case, whether you apply input at the inverting or non-inverting terminal, the output is neither increasing nor decreasing. It is settling down at a particular value. What is that value? We need to calculate, keep it aside. Whereas, if you have the connection, feedback connection from output to non-inverting terminal, what happens? Output is reaching its extreme values, plus V saturation or minus V saturation. Whether you apply input at the inverting or non-inverting terminal, doesn't matter. Okay. So, means this is an example for positive feedback. Okay, output to non-inverting terminal connection, this is called a positive feedback system. Okay, it is positive feedback system. Whereas if you have the connection from output to inverting terminal, what happens is it is a negative feedback system. Okay, I will write it in a separate page otherwise. Let me erase this. Okay, here place is not permitting, right? I will write here. We have three types of circuits. It is open loop configuration. Here what is the output? Plus or minus V saturation. I can write. And the second one is op amp with it is plus and minus. There is a connection. A part of the output is fed back to the inverting terminal R1, R2. Then you may apply input either at non-inverting or inverting terminal, doesn't matter. What about the output? Output is neither increasing nor decreasing. Here the key point is output is inversely proportional to V minus and V minus is proportional to V output, so that output is neither increasing nor decreasing. V output neither increases nor decreases. It is an example for negative feedback system. It is a negative feedback system. Whereas the third case, we have the feedback connection from output to non-inverting terminal. You can remember like this: output to inverting, negative sign, it's negative feedback. Output to non-inverting, it is positive feedback. You may apply input either at inverting or non-inverting terminal. Input may be positive or negative, doesn't matter. Here what happens? Output is proportional to V plus and V plus is proportional to V output. That's why the output will continuously increase or continuously decrease. Here also the output is either plus or minus V saturation, depending upon the input and at what terminal, what is the value of input and where you are applying the input, right? And it is a positive feedback system. Okay, in open loop system or with no feedback, already it is an unstable system, I can say. And to an unstable system, if you apply positive feedback, it still remains in unstable state only, and its output still remains at plus or minus V set. I cannot write output is equal to something into input here or here. I can mention it is unstable system, it got saturated. It gives its extreme possible values. That's it. Okay. Whereas with a negative feedback, output is neither increasing nor decreasing. It is settling down at a fixed value. At what value it is settling down, we need to calculate. Here I calculated perfectly, but here I have to make the calculations. Okay. Now I will. Right now, there are a lot of applications developed with op amp in open loop configuration with negative feedback and positive feedback. What are those applications? Means with negative feedback, if you see adder, summing amplifier, adder, subtractor, multiplier, divider, all those things, voltage to current, current to voltage converter, instrumentation amplifier, integrated differentiator, like that. And some applications with right negative feedback, and it's also known as linear applications. Why we are calling that as linear applications means here you can able to write output is equal to something into input, you can able to write. Okay, that's why it is a linear application we call. Whereas in these two, with open loop and with the positive feedback, output is plus or minus vsat. So those are called comparator applications we call. And some non-linear applications are applications with uh, right, positive feedback. Positive feedback means right, output is plus or minus v set. That's what it's called non-linear. You can't write output is equal to something into input. Or it's also known as comparator applications. Right, Smith trigger circuit, monostable multivibrator, stable multivibrator, triple five timer, etc. These are some of the applications. And there are some more applications of op amp with diode, BJT, GNR diode, etc. With right, RC passive components and all. Some more applications of op amp with diodes, BJT, FET are like waveform generators, like triangular wave generator, sine wave generator, square wave generator. Of course, monostable multi means it's a single pulse generator, and astable multi means square wave generator. Right? Waveform generator means sine wave, triangular wave, etc. Regulators, we studied regulators using diode, BJT. Now you will see the regulators using op amp. Active filters, there are some limitations with passive filters. To overcome those, we are going with active filters. And a precision rectifier or precision diode or precision rectifier or super diode, all mean the same. It means rectifiers using op amp. What is the advantage of these rectifiers with op amp compared to diodes or regular diode circuits? We need to see that. Again, peak detector, what is meant by this, which is mainly a communication related application, right? Clippers, clampers, sample and hold circuit, it is also communication related. Logarithmic, anti-logarithmic amplifiers, multiplier divider, A to D, analog to digital and digital to analog converter. This part you will be studying in digital, not in analog. Right? I will be covering these all applications in our analog circuits here. So, right, applications with comparator. Actually, comparator applications like zero crossing detector, triple five timer, you can see these are applications of op amp with open loop configuration. And application with positive feedback means mid trigger circuit, monostable, stable multi, and all you can see. Even waveform generators also we use applications. These are some of the applications of op amp with positive feedback. With negative feedback, enormous lot of applications: adder, subtractor, integrator, differentiator, so many things. We will discuss all these applications right in the next section. Okay, first I start with this applications with negative feedback. In this case, I said output is neither increasing nor decreasing. Yes, at what value it is settling down. That's what we are going to discuss.